Hello there, 8th graders. This is Mrs. Minowitz, and I'm here today to talk to you about the Milky Way galaxy and also about stars. One of the things that I want you to understand about space is this idea of dark matter. So dark matter is a type of matter hypothesized in astronomy to account for a large part of the mass that appears to be missing from the universe. Dark matter cannot be seen directly with telescopes. Evidently, it neither emits nor absorbs light. Instead, the existence and properties of dark matter are inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. It is thought that the total mass energy of the known universe contains 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy, which is a hypothetical form of energy that permeates all of space and tends to accelerate the expansion of the universe. So the main point that we want to get across here is that much of what we think the universe is dark matter. And this is something that we cannot directly see because it doesn't emit or absorb light, but because of how interactions between other things, our explanation for it is dark matter causing different impacts on things that we don't have the technology or a way to detect yet. So the galaxy that we are in is the Milky Way galaxy. That is the name of it. The sun is just one of billions of stars that are in the Milky Way galaxy. Our galaxy is very, very large. There's billions of stars in it, but there are also billions of different galaxies. So the universe is huge in comparison with our own solar system. Galaxies can also have different shapes. The shape of our galaxy is what is called a spiral shape. If you take a look at this diagram here, this is showing you roughly what the Milky Way galaxy looks like. Now, this is a diagram and not a picture. We cannot get a picture of the entire Milky Way galaxy. And the reason behind that is because we're inside of it. We can't take a picture of the entire thing from inside of it. If you think about it, it's like trying to take a picture of your house, the outside of your house, but when you're inside of it. It just doesn't work. So if you take a look at this diagram, you'll see that the Milky Way galaxy is approximately 100,000 light years across. The sun is here more towards the kind of the outer part. There's this big central bulge in the center. And what happens is things on the outside will move around the central bulge. One journey of our solar system around the center of the Milky Way galaxy is sometimes called a cosmic year. And that takes approximately 225 to 250 million years on Earth. Okay, so we are actually moving around the center of our galaxy. This is another depiction of what they think the Milky Way galaxy looks like, more from the side, where you can see this central bulge here that the things are moving around. We're going to start talking about stars now, and different stars that would exist in different galaxies. To discuss that, though, we need to talk about this idea of a light year, and we talked about that the Milky Way galaxy being 100,000 light years across. A light year, remember, is a distance. It is not a time, even though it has the word year in it. It is the distance that light travels in 1 year. That's about 9.5 trillion kilometers. This is also known as the speed, has to do with the speed of light. How fast that travels in a year gives us 9.5 trillion kilometers as the distance for a light year. One of the main points we want to talk about is with stars is that they have a life cycle and they go through different stages. So if you think about it, you have a life cycle, you go from being a baby to a kid to an adult. Stars kind of have the same type of thing going on with them. In order to understand how that life cycle works, we have to understand what's happening in the vast majority of our stars. So stars consist mainly of hydrogen and helium. And what's happening in most stars is that two hydrogen atoms fuse together to create a helium atom. And this process is called nuclear fusion. So we take a hydrogen and another hydrogen and they get pushed together and that makes them into a helium atom. Okay, this can only happen under certain conditions that do happen in stars. In order to figure out what happens next with stars after they're done fusing their hydrogen into helium, it depends on what the mass of the star is. So stars can be classified as low mass or high mass. They all start out as a nebula, and a nebula is a large cloud of gas and dust. So this is an example of a nebula. This is the Crab Nebula. So a nebula is where stars start or where they are born. After that, okay, if you look here, it's called the stellar nebula. More detail. Our sun would be one of the low yellow stars are concerned. However, again, when you compare the size of the sun to the size of the planets, it is much, much larger. So what's going to happen to low mass stars over their life cycle, which is about 10 billion years? They start off in what's called the main sequence, and that's where they're fusing that hydrogen into helium. This is 90% of all stars. This is where the vast majority spend their life. After that, when all of that hydrogen is used up, it starts turning into what's called a red giant, then a planetary nebula, and then finally a white dwarf. So I've got a video here that kind of shows you those different stages that it goes through. So we're starting off moving in towards the sun from the outer part of our solar system. So as you see, the sun is starting to become larger and larger. This is what happens when it becomes a red giant. It can't maintain everything as close to it anymore. So it expands in size. It would actually stretch out further than some of the inner planets. But that is not stable for a long period of time. So you'll starts to lose outer parts of it, and then it forms what's called a planetary nebula, as shown here. And then here at the end, its final stage for a star like our sun is a white dwarf star. So if you look here, the vast majority of time again is spent on that main sequence. This would not happen to the sun to move to the next stage for another about 5 billion years. And then after that happens, we would have the red giant, planetary nebula, and white dwarf stages. So red giants are about 10 to 100 times larger than our sun. And our sun has a radius of 700,000 kilometers. So it would be 7 million to 70 million kilometers large, anticipated. But in terms of different stars, our sun is small or average. On this diagram, it is 1 pixel compared to some of the larger stars, which can be as much as 600 light years across. So there are stars that are much, much larger. Those large stars, the high mass stars, they have a life cycle of only about 10 million years. Okay, much shorter than our low mass stars. So they do start off again in the main sequence. They fuse that hydrogen into helium. When that is done, then they start to move on to the next stage. They become red supergiants. Then there is a supernova, which is like an explosion. And then their final stage is either a neutron star or a black hole. Only the most massive of stars would turn into black holes. Less massive ones would become neutron stars. Still have a lot of mass, but not quite the very tip top would be neutron stars. Neutron stars are very, very dense. They get their name because their protons and neutrons, or the protons and electrons get squished together and they form neutrons. That's how they get the name. Due to the density of a neutron star, 1 teaspoon of it would weigh 1 billion tons on Earth. Very, very dense. According to astronomer and author Frank Shu, a sugar cube of neutron star stuff on Earth would weigh as much as all of humanity. It is very compacted material. Black holes, even more so. And we will talk much more about black holes in class. One idea, though, with black holes to understand is that there is a black hole at the center of the Milky Way galaxy, supermassive black hole. It has a mass equal to about 4 million suns, and it would fit inside a very large ball that could hold a few million Earths. So it is much, much more massive than our sun, the star that turned into this black hole. But its volume is small in comparison to that, so it is very, very dense. We will talk more about black holes in class.